welcome to the video. This is a lab number 4 demonstration for ELEC 291. So this is my lab 4 project, and so this is basically incorporation of analog to digital converters and temperature sensor and PWM signal generation using the EFM8 microcontroller. So as inputs for a sensor, I'm using a potentiometer to generate a potential difference, which is going inside the analog to digital converter of the microcontroller. And also we have this temperature sensor attached here, and this is basically the temperature. This basically senses the temperature and gives a potential voltage output depending upon the temperature. So here I have attached the oscilloscope. This is in order to view the PWM waveform output that we get from this black pin, and this goes into a MOSFET to control this. This is a cooling system, so I'm using a thermoelectric cooling pad to basically create a cool surface to measure the temperature. And this system is a heatsink, and this is a fan which I'm not currently using, so it's turned off. This material, when you apply voltage across this and this pin, about this and this pin, you get a temperature difference based on the voltage. So I'm applying around 12 volts that basically generates a temperature of around 15 to 16 degrees in this side, and a temperature of around 50 or 30 degrees, 50 or 60 degrees at this side. That's why we are using a heatsink. So let's demonstrate the lab demo. So the design is pretty simple. We have an LCD screen for output. Then we have 3 buttons to start. So I'm only using this, the second button, which is here, and the middle button. Then so it says press button 1 to start. So when I press this button, so right now it's at the PWM duty cycle mode. So the PWM is being the duty cycle of the PWM is controlled by this potentiometer. So if you look at the screen, we have the duty cycle output, which is around 98%, so it's almost 100% duty cycle, and that's why it says it's the duty cycle of around 98.62. So if I move this encoder, like if I go back, so you can see here the duty cycle is now 33%, and when you look at the oscilloscope of the output pin, it says you can see the pulse width is now changed. So now I'll be changing this potentiometer pin, and you can see the change on the duty cycle. So I'm increasing the potentiometer, which is increasing the duty cycle. Now I'm decreasing the potentiometer, so now it's almost 0. So the duty cycle is 1.5. Yeah, that's the minimum duty cycle I can achieve using my configuration. So now if I go back to full duty cycle, so now the maximum duty cycle I can achieve is 98%. And so this is basically used to control the output of this thermoelectric cooler. So how I am attaching is so my program measures the temperature at this point, and then it sends the data over using the serial connection to the computer, and then we can use Python to generate plots and view the data visually. But for now, let's show you. So right now I have it at 50%. I'll just go back and move it to 0%. So right now the PWM output is 0, and it's like almost 0. And now let's press the second button. So if I press this button, we'll shift the display to temperature measurement, and it says the current temperature is 16.9 and 17. So this is the temperature will be increasing, because earlier when I was talking about this the system, this cooler was on, and so this was cool. That's why the temperature had a less reading. Now it's increasing, so it goes up to 19, and it will go up to 19 slowly. And so let's configure. Oh wait, yeah, this is the multimeter. I'm using the multimeter to measure the current. More on that later. So let's measure the Python. output. So serial plot, the plot of the plot of the output. So the strip chart, I mean. Let's run the module. And so as you can see here, if it's clear, yes, yes, okay. So the red line, which is over here, is the temperature output, and the black line is the PWM duty cycle. It goes from 0 to 100%, and the temperature is also in the range, but it only goes from like 20 to 15. So you won't see that much difference in temperature. But if I change the potentiometer, have a look at the black line edges here. So as you can see here, the black line is now increased. So this means that we're almost at like 35 or 38% duty cycle. And if I change it up, it goes up again. So basically that's the PWM signal. So the duty cycle is also being plotted in with the temperature. We have a axis labels over here. So measurement temperature, temperature is in red and duty cycle in black, and then the time. So the measurement value are given in every 250 milliseconds. So that's the update time. Now let's see the temperature. So when the duty cycle is 0, the temperature is around, so it takes a little bit while to go back to the original temperature, but it's around 17 degrees Celsius, and we can see that on the plot. Now let's slowly increase the duty cycle. So now the duty cycle is around, so I put it on 60% duty cycle, and the temperature now is starting to go down. So you can see the chart now. And so as you can see, the temperature is slowly going down as we know that the minimum temperature achieved with my current settings of the thermoelectric cooler, it will only go to about 15, which is difficult to see. But if you can see, right, we are actually moving a little bit down, and the temperature measurement is now 16.39 degrees. So it's constantly decreasing. Now let's put the output to full 100%. So yeah, so now we have the almost 100% output of the PWM, and this thing is actually now at full power. So if I touch it, yeah, it's really cool. It's cold. The temperature is around 15 degrees. Yeah, the temperature is around 15.8 degrees, and this plot is now here. So yeah, earlier, if you happen to notice, the temperature was around somewhere over here, and now it's around here. So we see a difference of about 2 degrees centigrade. And now I'll just suddenly stop the output. So as you can see, it dropped to 0, and now we should see an increase in temperature. So right now the temperature is about 15.9 degrees, 16 degrees. So this takes a little bit time to go back to the original because the heat has to radiate outward and it needs to become hot. So it will take a little bit time, but as you can see in the graph, yeah, so you can see it is increasing slowly over here, and we see a spike, like a slope of going upward, and that says that temperature sensor. If I touch the sensor, so I'm touching it, and the temperature is around 18.9, 19, and 50, 19, 21, 20, and in the chart you can see it goes up, and that's the maximum it goes because that's the room temperature. Yeah, so when let's talk about the MOSFET driver that am using to control the output of this thermoelectric cooler. So when the PWM signal goes from here to the MOSFET's gate, and then the input, which is a wall adapter, this is going from here, and I am using the multimeter to measure the current. So when we have almost 0 duty cycle, the current drawn is around 8 milliamperes, and when we have about 100 duty cycle, so the maximum current drawn is around 171 170 milliamps. It's a bit yeah, it's fluctuating a bit, but it goes to 170. So that's the current draw at max settings. And though I have added a small diode because of the fan that I was originally planning to use, but since I'm not using it, it's just there. Yeah, so the MOSFET basically controls the amount of voltage or the power that goes inside this thing, and ultimately using controlling the output of the cooling, the coolness. Quick update. So right now I'm using this power supply, which is giving me a current of around 0.6 amps, and now the temperature is, as you can see, quite low. So earlier it was this, and right now it is around 10 degrees. Yeah, so this is using this system, and yeah, so let's switch it off. So right now I'll go back and go to set the duty cycle to down. So oops, yeah, so right now duty cycle is now, and the temperature will increase, and I should probably remove this power supply because it's going to heat up the MOSFET. Yeah, so you can see the temperature now going up, and this is when I use the full power of this thermoelectric cooler. And with this we can also use this to make a temperature controlling system that will maintain the current and the set temperature using the PWM signal. So this can be a further topic of interest for research or like another project. Yeah, so thank you for watching this video. I hope you liked it. Yeah, I'll see you in the next video then.